Okay, let's unpack this. Today we're diving into a journey that sounds deceptively simple, really, taking a brilliant product design concept and transforming it into a physical injection molded reality. You might have an incredible market-disrupting idea, but that path from a beautiful 3D model to thousands of identical perfect parts coming off a press, that's where the real challenge often hides.
And that challenge, well, for so many designers, it turns into costly mistakes and, frankly, frustrating delays. Our mission today is to equip you with the insights you need to navigate this journey smoothly, making sure your design isn't just functional or, aesthetically pleasing, but truly engineered for manufacturing success. We've gathered insights from Justin and his team at True Position Plastics, a group whose expertise is rooted in a pretty unique 360-degree view of this specialized world. They're going to show us what it really takes.
And what makes Justin's perspective so valuable? What truly sets True Position Plastics apart? Well, it's that his expertise isn't born in some theoretical vacuum, right? It's forged right there on the factory floor with his hands in the steel, actually building the molds himself.
That's the critical difference, yeah. Justin actually started his career as a mold maker. Think about that for a second. He spent years meticulously crafting and repairing these high-precision injection molds. We're talking tolerances tighter than a human hair, plus or minus what? 0.00002 inches, using specialized gear like surface grinders, EDMs, electrical discharge machining. He mastered these incredibly intricate techniques like spotting, that's hand-fitting rolled component with extreme precision. You need that for a perfect leak-free seal. This hands-on background gave him this intimate, almost visceral understanding of tool steels, coatings, heat treatment, and exactly what it takes to make a mold work.
Okay, wow. So he knows the mold itself inside and out, the very heart of the manufacturing process. But then he made a really smart move, right? Transitioning to mold design. That's a huge bridge for designers like us.
It is, absolutely. From building, he moved to designing hundreds of diverse molds. And not just the simple ones. We're talking complex types like unscrewing molds. You need those for parts with internal or external threads, which are notoriously tricky to get right. Or overmolds, where one material is molded over another, like those soft touch grips we see everywhere. His skill in SolidWorks and Fusion 360 isn't just about knowing the software clicks. It's about applying that deep mold-making knowledge to spot problems right there in the 3D CAD model, way before any steel is even ordered. That foresight, well, it can save clients astronomical sums.
And his journey didn't stop there either. He then scaled up, becoming a global tooling manager, overseeing entire tool builds not just locally, but overseas, places like China, Taiwan, Malaysia. That's a significant leap, dealing with different cultures, communication styles, manufacturing environments.
Oh, absolutely. In that role, he steered projects through every critical phase. From the initial DFM reviews, and we'll definitely dive into DFM to T1MP process validation, which is all about making sure that very first batch of parts off the production line are perfect and that the process is rock solid for potentially millions more. He supported press-side molding for first articles, basically being right there as the initial parts were made, ensuring quality. This global experience means he's seen how design choices play out, from a CAD file on a screen to a finished product thousands of miles away, and across countless industries too. Consumer, medical, automotive, electronics, industrial stuff.
What's truly fascinating here is how all these diverse experiences connect, isn't it? It's not just a list of jobs on a resume. It's this progressive 360-degree journey that gives Justin and True Position Plastics this incredibly rare, holistic perspective. They've literally lived in every corner of this process.
That's exactly it. This comprehensive background allows them to uniquely translate between the often abstract language of product design and the very concrete, unforgiving language of tooling and manufacturing. They don't just understand what the DFM rules are, they understand the real-world outcomes, the costs, the delays, the quality issues that happen when you overlook them. It's hard-won, practical wisdom, really.
Which brings us perfectly to design for manufacturability, or DFM.
Yeah, with that kind of background, it makes complete sense that DFM is such a cornerstone of what True Position Plastics offers. It seems absolutely critical for avoiding those hidden costly mistakes and, ensuring a smooth production process. They're giving you insights derived from actual molding outcomes, not just textbook rules. And this raises a really important question for designers. What does DFM truly entail, and why is it so vital? Essentially, DFM is an advisory service. True Position Plastics proactively flags potential problem areas in a structured report, offering feedback and practical solutions. But it's crucial to understand this. They're not product designers. The final design changes, the final decisions, those always remain with you, the design team, so your original design intent isn't compromised.
Okay, so beyond just pointing out, hey, there's a problem here, what kind of specific issues are they consistently flagging, things designers might easily miss?
Well, one thing many designers, especially those pushing aesthetic boundaries, often overlook is what Justin calls the hidden draft tax.
Hmm.
Insufficient draft, that slight taper on vertical walls so the part can pop out of the mold easily is a huge culprit. You generally need a minimum of about 1 degree for most resins, maybe up to 3 degrees for textured surfaces or really deep features. True position plastics found that even a seemingly minor oversight, like maybe half a degree less than optimal draft, that can quietly add seconds to your cycle time. Over 1 million parts, that adds up. We're talking hundreds of thousands in unnecessary production costs, a hidden cost nobody budgeted for initially.
Wow, that's a really concrete example of how a tiny design detail can have massive financial ripple effects. What other common traps do they identify?
Oh, they're constantly on the lookout for undercuts features that would physically stop the part from ejecting from a simple two-part mold. Now, undercuts aren't impossible to deal with, but they require complex and expensive side actions or lifters built into the mold, and that drives up tooling costs significantly. They also spot things like inaccessible ejector pin zones, parting line conflicts where the two mold halves meet unevenly, and critically, sharp internal corners. Those are bad news. They act as stress risers, weakening the part, and they also impede the smooth flow of molten plastic. And of course, gate placement. If the gate where the plastic actually enters the mold cavity is too far from flow critical features, you're basically asking for trouble with filling and overall part quality.
So it's not just what they identify, but the ripple effect, why it matters, and how it impacts the bottom line, the cycle time, the quality.
Exactly. True Position Plastics understands precisely how your part geometry, the gate strategy, your chosen resin, and the tooling decisions all kind of interact to impact those critical outcomes. Things like yield, how many good parts you actually get versus scrap cycle time, and cosmetic appearance. They provide specific, actionable suggestions grounded in global SPI standards, deep knowledge of resin behavior, and your specific production intent. This proactive feedback significantly cuts down on costly mold revisions and prevents delays. That's incredibly beneficial, especially for early-stage concepts coming out of industrial design firms.
Okay, so what does this all mean for you, the designer, sitting there with your latest concept? Let's break down some specific design considerations that True Position Plastics really prioritizes, essentially giving you a kind of roadmap to a truly moldable design.
Yeah, let's dive into some specific areas where designers often run into challenges. And importantly, how True Position Plastics provides practical, real-world solutions to make your parts not just functional, but truly ready for manufacturing at scale.
First up, material selection. This isn't just about picking a material that looks right or has the right properties on a datasheet, is it? It's really about understanding how that material will actually behave under heat and pressure inside that mold.
Absolutely. The crucial considerations start with matching the material to your functional needs. Things like temperature resistance, mechanical strength, maybe chemical exposure, UV stability, basic stuff. But then you absolutely need to factor in its processing behavior. For instance, semi-crystalline resins like PBT or nylon, they contract quite a bit when they cool. This can lead to non-uniform shrink and warpage, which can be a real headache. Whereas amorphous resins like ABS or PC, they tend to offer better dimensional stability, but often have lower chemical resistance. Trade-offs.
That distinction alone sounds huge for just predicting how your part's going to turn out dimensionally.
It really is. Then you factor in moldability and the actual part geometry. Some resins, like, say, polypropylene, PP, flow easily into thin walls. Others might need larger gates or higher injection pressures to fill properly. And you can't overlook fillers and reinforcements either. Additives like glass fiber, sure, they boost stiffness, but they can create anisotropic shrink, which just means the material shrinks differently in different directions. That can really throw off flatness and the precise location of holes. Justin and his team help designers make informed choices here by reviewing resin datasheets, maybe running flow simulations, and advising on these subtle behavior risks based on your part's specific geometry and application.
Okay, next let's talk about wall thickness best practices. This sounds deceptively simple, maybe, but it sounds like it's a huge, silent quality killer if it's not managed properly.
Oh, it's absolutely critical. Wherever possible, uniform wall thickness is just paramount. Ideal ranges for common materials like ABS and polycarbonate PC are typically maybe 0.060 to 0.14 inches. Nylon and PVT are often a bit thinner, say 0.040 to 0.120 inches. Interestingly, LSR, that's liquid silicone rubber, that allows for much thicker walls because of its unique flow and curing properties, it's different. But the key in most nanoplastics is really to avoid excessively thick walls. Anything over, say, 0.150 inches, you're risking sink marks. Those are depressions on the surface as the material cools and contracts, or internal voids, or just excessively long cooling times unless it's properly cored out, hollowed out.
And it's not just about the absolute thickness itself, but how it transitions, right? Going
And
from thick to thin sections.
precisely, you need to transition gradually. True position plastics advises tapering thick to thin transitions at maybe a 3-to-1 or even 4-to-1 ratio where possible. Sudden, sharp changes cause hesitation in the material flow. That can lead to weld lines and other cosmetic defects. And for strength, instead of just making walls thicker, they often recommend using ribs or gussets for support. These should typically be about 50 to 70% of the nominal wall thickness, and you want to space them maybe 2 to 3 times the wall thickness apart to avoid those pesky sink marks showing up on the opposite side of the part. Justin and his team will call out these thick sections, the risky transitions, any problematic rib configurations during those DFM reviews. That lets your design team adjust things before tool design even kicks off.
And when we talk about those thick to thin transitions in cooling, there's some interesting physics going on there that directly impacts the final part, isn't there? You mentioned sink marks and voids.
There absolutely is. Think about it. In thick regions, the molten plastic simply stays hot longer, much longer. This directly translates to longer cycle times, which, hits your production cost. It also significantly increases the risk of those sink marks or internal voids we talked about. And crucially, it creates uneven packing and shrinkage across the part. That's a major cause of warpage, where your part comes out bent or twisted instead of flat. So to mitigate this, standard design guidelines suggest coring out thick features, anything over about 0.150 inches. Always transition from thick to thin, never the other way around. That causes problems. It's also smart to place gates closer to the thicker regions to ensure they get packed out properly with plastic and prevent underfilling. And critically, avoid trapping heat in isolated spots, like don't put a big logo boss right on top of a thick solid dome feature. That's asking for trouble. True Position Plastics identifies these problem areas during DFM and often runs simulations to confirm material flow and cooling, making sure these issues are caught early, not after you've spent a fortune on the mold.
Okay, so how do we know? How do we know if these complex design choices, material, wall thickness, gate placement, all that stuff, will actually work before we start cutting expensive steel? This is where simulation comes in, right? Mold flow analysis.
That's exactly where mold flow analysis becomes such an indispensable predictive service. True Position Plastics offers this, and the timing is key. You absolutely run this before mold design begins, usually after your general part geometry is pretty locked down. You never, ever want to discover these kinds of fundamental flow problems after the steel has been cut.
Yeah, I can imagine why that would be a complete nightmare. So what crucial insights does a mold flow analysis give you as a designer?
It reveals a treasure trove of information, really. You'll see fill time and pressure distribution across the part. You'll see exactly where weld lines and air traps are likely to form. Those can be weak points or cosmetic blemishes. It shows gate freeze timing. Knowing precisely when the plastic solidifies at the gate is critical. It dramatically impacts how the rest of the part fills and cools. For glass-filled resins, it even shows fiber orientation, which is crucial for predicting structural integrity and warpage. And perhaps most importantly, it provides pretty accurate warpage predictions, highlighting cooling uniformity issues and potential hotspots in the mold. Mold flow analysis is essentially your crystal ball. It helps you avoid costly tool modifications by verifying that your gates, vents, wall transitions, that they'll actually function as intended. True Position Plastics uses advanced software like Autodesk Moldflow or Moldx 3D, and their team walks designers through the results. They effectively bridge that gap between your design intent and the cold, hard realities of tooling and the molding process.
That sounds incredibly powerful. So beyond these specific technical deep dives on materials, walls, simulation, are there other general golden rules, things that everyone designing for injection molding should just keep top of mind?
There are indeed several general best practices that True Position Plastics consistently advises on. We already hammered on draft angles, minimum 1 degree for vertical faces, maybe up to 3 for textured surfaces or deep draw features, essential for ejection. Next, always support structural features properly. Bosses, for instance, those posts often used for screws, should always be supported with ribs or gussets. Avoid free-floating thick bosses. They will inevitably lead to sink marks on the cosmetic surface opposite them.
Right, that makes perfect sense. You're basically providing a structural skeleton to support those features and manage the plastic thickness.
What else? Minimize sharp internal corners. Try to use inside radii of at least, say, 0.015 inches, maybe even more if possible. Sharp corners concentrate stress in the part, making it weaker, and they also resist the flow of molten plastic during molding. Not good. You also need to actively design for ejection, avoid features that might stick in the mold or create suction effects, and ensure you have proper flat surfaces for the ejector pins to push against without damaging the part. And finally, something designers often forget. Consider tooling access. Don't bury fine details on shut-off faces where mold halves meet, or deep down in pockets of steel. That makes the mold difficult and expensive to machine, polish, and maintain. And always be aware of the limitations of things like lifters and slides. Those mechanisms for handling undercuts, they have limits on travel and complexity for the mold shop. True Position Plastics helps ensure your part isn't just functional on paper, but truly moldable in practice, setting realistic expectations of what's genuinely possible on the press.
Okay, this has been an incredibly thorough, really useful deep dive into the complexities of injection molding. So to bring it all together, what does True Position Plastics do for designers? Specifically, to make this entire process easier and more successful, how do they act as that manufacturing navigator you mentioned?
Yeah, Justin and True Position Plastics' core value proposition is really about partnership. And it's important to clarify again, they are not product designers. That's not their role. Their primary function is to support product designers and industrial designers with that crucial manufacturing feedback. But without altering your fundamental design intent, they are there to help make your vision manufacturable, not to redesign it for you.
Got it. So they're like your experienced co-pilot, guiding you through the sometimes treacherous waters of manufacturing reality.
Exactly. That's a great way to put it. Their range of services is pretty comprehensive. Mold flow analysis, those detailed DFM reviews we discussed. Also, tooling sourcing, whether you need tools built onshore, here, or offshore, specifically mentioning their experience in places like China, Malaysia, and Taiwan. They also provide process optimization and validation, making sure the molding process itself is dialed in and perfected for consistency. And even press-side startup support for the molders, helping ensure that critical first production run goes off without a hitch. The bottom line is really this. A great design, no matter how innovative or beautiful, can still fail miserably in production if it's not moldable. True Position Plastics helps ensure your part makes that journey smoothly from concept to molded reality without those costly late-stage surprises. They provide fast, accurate DFM feedback with practical solutions and, importantly, proven judgment on what's truly worth fixing versus what's actually fine and manufacturable as is.
And I understand they even take it a step further with something called scientific molding. What's that about?
That's right. So beyond just making a part moldable, they often implement a scientific molding approach. This involves using techniques like golden sample methodology with design of experiments, or DOE. They do gate-freeze studies, implement decoupled molding principles. It's a more rigorous data-driven approach. It's about more than just making a part. It's about optimizing the entire molding process for repeatability, reliability, and true production readiness. It's really how you achieve consistent, high quality at scale, part after part, shot after shot.
Okay, this has been an incredibly insightful deep dive into what it really takes to bring a design to life through injection molding. I think the key takeaway for you, our listener, is really appreciating that intricate and often invisible dance between your design vision and the physical manufacturing reality. Your brilliant concept needs to speak the language of the factory floor, and that's where expert guidance like that offered by True Position Plastics becomes just immensely valuable. So what does this all mean for you as you develop your next product?
Well, in a world where we can visualize ideas almost instantly on screen, the true magic, and often the real challenge, lies in understanding the hidden physics and engineering required to bring those ideas physically into existence. So maybe I'd like to leave you with this thought to ponder. How might you rethink and integrate these manufacturing considerations into the earliest stages of your design process, knowing now that every curve, every wall thickness choice, every material selection tells a story on the factory floor long before the first part is ever actually molded?
A truly powerful thought to mull over as you design your next innovation. Thank you so much for joining us on the Deep Dive.